How's it going, everyone? Welcome. Gabriel Gonzalez here. So today let's gonna continue exploring about the topic of least exposure as a way to understand the author intention, Kyle Simpson, of why he thinks that this is important. Because when I and you, if you are watching this, explore about that, so it'll make much more sense to now when you are writing a code, when somebody tells you to implement a particular feature, uh, you know how to do that, what to do, and why you're doing. And I do think this is very, very important because what you do in uh, what you do in where you do it matters much more how hard you do it, right? So this is also speaking in terms of, hey, if you're working for an X company, whatever company it is, okay, it is important to know what you are doing in that company, what is the role that the company is looking for. So for example, a JavaScript developer or a web developer, an Angular, React, Vue, you name it. But understanding is what is the value that you are providing to that company, and understand also the business model. Okay, so this is one of the beautiful things that I do think, as somebody that works with computers, as a web developer, we have the blessing to understand and have the time to work behind a desk, because we can also dedicate time to explore these ideas and also living the day-to-day existence. Now, on that topic, all right, so this is the reason why we are going to look at the least exposure, at least on this chapter, okay, which is describing is, or which is something that Kyle Simpson, as I mentioned before, mentioned. All right. So to understand how do we get here, I'm gonna make a quick recap, which is by asking the question of what is JavaScript. I do want to know what JavaScript is and how do we get here in 2025, right? October 10, 2025. Because that'll make much more sense when you need to explain how you do that, why you do that to your clients, right? Even to your manager, to whoever is going to hire you. You know how to do that and why you're doing that, right? So, because JavaScript is not only based on the technical aspect, which is very interesting, and I am here based. I'm here is on the on top of the giant shoulders, which is the hard work of all of this individual women and men that has now collaborated through history over centuries to now I can speak this kind of BS, all right, or to speak now here this all of this fluff to make sense of how do we get here. Now, in order to quickly understand how do we get here again, is first understand what is JavaScript. So that's what we look in the several videos, in the past several videos. So what is JavaScript? Who made JavaScript? What now is the role of JavaScript? So who oversees right now is JavaScript, technically, right? Which is the TC39. Now who owns the legal trademark of JavaScript? all of this are aspect that are around JavaScript, right? That are around the technical aspect of JavaScript, as well as what is the stage or the process that the TC39 does when it comes to add features or to update them. All right. So, for example, is well, anytime that you want to use a particular feature or you have an idea that would like to be part of the JavaScript. So, for example, how do you deal with eventual values or to a sequence of eventual values? Right? You will have now promise and observables and what these concepts are and how to do that and what are use cases. So this is now a stage or a series of stage that a particularly champion or a proposal need to go pass through all the way up, right? And it is made of 5 stage from 0 to 4 because we are programmers started to count from 0. And also I look at how now can we guarantee, as you imagine that you are part of the TC39, that the web doesn't break, right? But you can guarantee this backward compatibility. So that's why they provide now polyfills, and that's what the polyfills means is a shim that you can now put in your code to guarantee that. And also is the other environments that we can now JavaScript. So for example, because JavaScript by de facto can be run in the server and in the browser and even light bulbs and robots, the only reality that matter is the web. And that's what you can look at the spec, right? So based on that, because we have now, for example, is the developer tool that allows us to actually quickly access to this JavaScript engine. This is not a spec compliant to, and you can look at that. For example, when you use now they use a strict mode, all right. So this strict mode is a set of good rules that developers must follow to have a good chance for the JavaScript engine of optimizing and running your code, right? So also we understand that how JavaScript works. So what is the mechanism and how JavaScript behaves right now? And that is, well, the JavaScript in itself act more like a compiled language rather than an interpreted or a scripted language. So because right now in 2025, when you write a code, when that file leave your text editors, it's gonna be transpiled, aka it's gonna be converted into a browser safe code that then is going to be bundled up to, ready to be delivered. And when now somebody on the web call to the website, is going to be served that to the client. In this case, let's going to assume the JavaScript engine on the browser. It detects that, is going to parse that, aka transform that into an abstract syntax tree, which is an internal representation of how the code looked like for humans and for machines. And then it's going to generate now, and then it's going to pass the pen of the JavaScript engine through a series of process to run further optimizations by using the profiler and the internal compiler, and ultimately now run your code. So this is something that, for example, the V8 engine, which is a predominant engine that is on the market, in the web market, all right, is something that we can look at how the things works by By exploring is how it behaves in certain scenarios. So, for example, how it analyzes syntax errors, or how it give it to you now early errors before the code executed, as well as how now it do something called hoisting. Okay, so again, just to make a quick recap of that, we also look at the web assembly. That at the end of the day, this is as a language that allows to describe is without the high level language and skipping the parsing phase, uh, code that the machine now can directly execute in this particular environment, was environment. And there is some history upon that. For example, with ASM, I am not going to dive into in today's video, but I do think that this is quite revealing in terms of web assembly doesn't want to overthrow the JavaScript, or it's not gonna replacement of JavaScript. It's just an environment that now is very convenient because it is a universal compiler. So you can now take code from different other languages, right? And then compile to this intermediate representation of binary code known as WebAssembly that looks like an assembly code, all right, where you need to move its register to do certain operations, basic operations. So, for example, like addition, subtraction, division, and multiplication, basic arithmetic. And then, well, your code is now executing in this particular environment, in this WASP environment. So speaking of that, right? Speaking of places where we can run our code, particularly in JavaScript, we have now programs, okay? And this is now looking more at the technical aspect of JavaScript, which say, hey, well, we need to understand is how our programs, what is a program, and what is the anatomy of these programs. So by understanding is how a program to work in JavaScript, and how now JavaScript make all of these different standalone JavaScript files to cooperate at runtime by sharing the states or using the ES6 models. We also look at now that the program anatomy, which is made of statements, declarations, variables, and values, and especially values. So what is a value? What it represents a value in a program, which is a particular state that your program will be or is, all right? And this type of values is, well, at least in the JavaScript, is you have now Boolean to represent true or false. You have now a string that actually follow is a specific implementation of that, and that is the Unicode, which is a universal format, universal transformation format that has now a table that say, hey, this sequence of instruction, this sequence of zeros and ones, all right, or this sequence of bits, 16 bits, now represent is this symbol, and so on and so on. This is how you do a letter A, a letter B, a letter C, and so on and so forth. Not only Western symbols, but also is hand-based characters, Chinese characters, so Korean, Thailand, also is the Middle East, all right, Farsi. Sorry if I don't remember all of those. I am more exposed to Farsi, and even Mongolian, all right. But the point is that this is how we can now use this particular value to represent this, as well as numbers, and how it goes and it use the IEEE 7054, which is a fancy way to say, hey, this is the format in which we're going to represent value. So this sequence of bits, zeros and ones, now is going to represent number from it represents number for 9, a 9 followed by 16 zeros, if I recall that grade, right? And you may wonder what happens if you have now more numbers than that. Well, we have now another type of value known as big int that allows to represent much more values in that, and also some nuances that happen in that particular representation, especially with 0.1 and 0.2. All right, and why this is important, because at the end of the day, since in order to represent accuracy of our numbers, all right, so for example, it's like, how do you divide, what is the result of dividing, let's say you have a pizza, bro, okay, and then you want to make sure, and you have a pizza and you hang out with two friends, right? And then you want to know is how to share this pizza in equal slice, right? So if you, for example, now divide 1 times 3 in the decimal representation, all right, which is the number that go from 0 to 10, 0 to 9, all right, the question is that how do you now make sure that you're going to be very maniac to truly represent, to accurately represent is that slice, so each one of your friends can actually eat exactly that. And it turns out that, well, when you divide 1 by 3, it gives you now is 0.333333, and the more you continue to compute that, the more 3 gonna get you. So because our memory is limited, well, we need to somehow is to make that fit here. And our memory is like, you have a, imagine that you have now your pockets, right? Your pen pockets. Your pen pockets has a very small size. So if you want to store a lot of things, it won't let you. So I would like to now store is a car. All right, I would like to download a car and then put it into my pen pocket. But that's not how physics works, you know? And because of that, since we cannot right now accurately represent all of these numbers, we cannot fit all of these numbers in this particular pocket, all right? So we just chop up that number, right? And they say, hey, this is what you're going to be here. And this is why we have now this inaccuracy. Again, all of this is because our memory and the physical constraints of the memory, the place where we now use to store stuff, is quite hard. So if you imagine the diskette or all of this storage that we have been used over the past 30 years, that say, hey, look at this in from a diskette to now USB flash memory or USB flash drive, you see that there is now an increase in space exponentially, because now scientists, women and men, actually figuring out to now is increase the size that we can put stuff in a very tiny place, all right, at an atomic level. That's where we're getting closer to. And I do think that's mind bending. Mind bending stuff. So, in any case, so this is a good illustration of, well, the numbers and what we can represent with numbers, also the kind of emptiness. And here's when we get more philosophical. Is like, hey, what emptiness mean? All right. Do we mean it's absent of value? Do we mean that we don't declare something? So this is what it represents. So undefined and null. And the other is symbols, to use now this hidden private values that is not going to be exposed, not even to developers, but we can use this for hide some informations. For example, low-level models or frameworks that somehow needs to keep track of elements or that a particular sequence works as expected. So in any case, so again, this huge overview of these values, that also object is a type of values, and this object can be an array, and this object, and inside of this array, we can now put is primitive values that I mentioned, as well as the functions. And this to me is quite mind bending, because this is the things that I recognize that React and a lot of this smart folks say, hey, you know what, let's go to now reuse and understand is the JavaScript in itself, the core in itself, rather than reinventing or adding more layers on top of this, right? So because now functions, we can now hold them inside of variables, these containers, and it makes a lot of sense when you see things like that. So these variables or these containers we can use to now store values and what they represent. This is the history of software engineer. What all of the things represent is the representation. How can we now make these representations in a particular problem? And I do agree, well, what Grady Butch, a software engineer, that actually say, hey, you know what? The history of software development is rising one's level of abstraction. So the decisions that we need to make today are not based on the system designs, because all of those decisions that were made for us are now embedded into these frameworks. So the question is that now how can we, so the question is moving to what servers do I need, what cloud servers do I need, what cloud servers do I need, what platform do I need to go with. It's more now an economic incentive rather than systemic or rather than system designs problems. So yeah, I know that I take a quick tangent here. So by looking now at these particular values that I mentioned, and especially functions, and how function here is something that the language allows to held as a value, is very important to understand what functions can represent. And this is when I would like to later on is, well, do some coding here to say, hey, let me now is understand how can represent, how can describe problems using now JavaScript code or code in general, all right? But it turns out is that, right? Is this particularly values, function is one of them, and how now functions allow us is to describe that. So JavaScript in itself with functions that allows to describe is this sequence of instructions inside of this enclosing scope is something that when you now in the particular in JavaScript you declare a function or you now define a function and assign that to a value, that's two different behaviors. And JavaScript treats them differently, right? Known as function declaration and function expressions. So also we look at the all the things that we can do with these values, all right, such as comparing that or transforming, coerce that from one value to another, and what is the algorithm that is using behind the scenes, these abstract operations, which is a fancy way to say, hey, this is the series of steps that I'm going to do when you are comparing values or convert one value to another value. All right. This is something that you can take a look at the MS script. And also is, well, let's take a look at how can we now organize our code. That I do think this is the reason why I'm doing this exploration of limiting scope, exposure, and so on and so forth. Again, I'm brief and talking about a huge overview, okay? Describing is the anatomy of the programs, the values, what are the type of value that we can have, why functions are important, and the way of how you can now play with these values or the kind of operations that you can do on these values, and how you can organize your code the way how now JavaScript provide you. Again, the way how now the creator of the JavaScript, as well as based on his experience, how now the code can be organized, right? Whether it is in a function or in a model or in a class, all right? And what are the trade-off of each one of them, right? And also going deeper into these low-level features, right? For example, like iterations and iterables, iterators, right? Why do we have that in the language? And why do we have this convenient way to iterate through a sequence of values or these huge data sets? Also is, well, how can we now look at the anatomy of this particularly values, specifically functions, okay? Such as, well, how now variables inside of a functions are resolved to its identifiers, right? AKA the scope. And how now, for example, you in a function can have access to variables from the outer functions, even though that function was executed later on in the code, right? Known as closure. And also is the particularly property that function have, again, exploring now the anatomy of the function values, that is the value of this. So it allows you to expose now what the execution context has at that moment. So this is why it matters how this function it calls. Okay. So again, this is now properties or of the functions. And when you look now at the anatomy of another value, so for example, the objects, well, it has now this particularly mechanism, which is the object prototype change, which is a way of how now objects resolve property access, and if it's not there in that object, it's going to delegate to other objects via this reference to search for that property until it find or it reach to the top level object, all right? That is usually the object that points now to null that prototype. There is no reference, so I don't reference. Now, this is the end, bro. This is the end, girl. This is the end game. And when you combine now the ability to resolve property dynamically, okay, using is the prototype change with this keyword, which allow you to now is have access to these specific objects when this function is called, all right? So it matters how this function is called. So you can now is enhance dynamically the feature of your applications with this object property linking, all right? Which is at the end of the day, that's why we are looking at this, because we're going to build now products or maintain products, okay? So if you want to do any one of them, you need to add some features or know how to fix some features, all right? So update them or perhaps eliminate them, right? So in order to now enhance that features with the object prototype change, you can actually do that. And if you do that, right, as you now increase more and more functionalities to your application, then when that function is called, how do you actually make sure that you get the data that you needed? And this is why at runtime, right? And this is why, for example, this revisited or this keyword is something that is quite compelling. Again, this is something that is way much more powerful when you see that now as an example to do that. Even though that I looked at example, I barely understand that. So this is also go for another video. But in any case, so all of this is just to describe is the features of JavaScript. All right. So in today's video, what I really care about is now understand the scope. One of the features of the JavaScript, especially this low-level feature, is the scope. All right. So this is when we go through understand that JavaScript it is behaviors and why JavaScript behaves now like a compiler rather than a scripting language. Why this is important to actually understand that, because the more you understand the behaviors, the more these models describe the reality, the more able you will be to predict what will be the outcome. In this case, the JavaScript behave like a compiler language because of how now it analyzes syntax error. This is the observable behavior, analyze syntax errors, as well as how now it detects some early errors, all right, and also is the hosting and what hosting is, right? So in order to understand now this, we look at some metaphors that are helpful to do that. So anytime that you define now a function, it's going to create now a particular scope. The same for the block. In this particular scope is now when the variables are going to live, and also how this variable can have access to. And in order to align to how the JavaScript behave, because also our minds work with story, it makes sense the world through stories. So the more your story are aligned to the reality, to the true, the better off will be for you. All right. Uh, well, uh, mm, exactly. Well, um, for example, in this case, you can think of the way of how JavaScript behave like two phases. It has now the compiler phase and the execution phase. So this compiler phase is for certain functions declaration, certain declarations, which is something that we're going to explore that here. It now is say, hey, I'm going to is uh, act like a compiler when I analyze the code for these particular declarations, functions, var, let, cons, classes, and objects, uh, and I'm going to now I'm going to analyze this code to resolve it is identifier with these variables and functions first, okay? And then I'm going to now execute the code. So, but in any case, this is known as the lexical scope illustrated. And then we get into what really means is this lexical scope. So with these function declarations and block, and how these function declarations behave when you put now variables and let and cons, similar for the block, all right? And also some other scopes that are implicit. So for example, parameter scope, that to me was quite my bending. And when you look now at the functions, uh, it's also that functions are held, so functions can be is declared or can be assigned to a variable, and each one of them has their own behaviors. And because we can also look at another way to define function, which is the arrow function, and how that behave, and why we prefer, or at least this is more like an opinion, but why do we prefer to use now function name declarations rather than anonymous functions? Because we can now is target that lexically, all right, at this compilation phase, and also we can see what this function is doing. We can now understand what this function is doing. So, because this is the particular scope that we look, also the global scope, all right, that allow us to say, hey, this global scope is now, or any scope at the end of the day, is now a place where we can now is make different variables that can hold now values or instructions, okay? We can help them to cooperate with others variables or other set of instructions in that enclosing scope. So traditionally in the global scope, the way of how can we cooperate with other functions and variables is, or by sharing is the global, by using is the ES6 models, all right? This is something that is now recently, and also is to enclose that particular functionality in a function, all right? And inside of that function, you define now your variables that helps functions that describe is functionality in a models. So for example, hey, this is now the navigator API. This is now is the crypto API, the DOM API, so on and so forth, but only in this enclosing scope. And the other is by exposing these variables via the global scope. So we also explored about the different global scope. So for example, the browser, and how now at least on the browser this behave, okay, which is, hey, this is now how in JavaScript, all right, or at least in the global scope, this is the behavior of the global scope when you define now variables, whether it's a function, a var, let and cons, and also how you can now is do something known as shadowing, which is answer the question. What happens when you have now variables with the same name at different levels and different nested scope? Well, what it's doing is now shadowing, aka you cannot have access to the previous reference lexically, all right? You can create a copy to the previous variables to access to that, but you can have access lexically. So this global scope, we also look at the other global scope. So for example, like the developer tools, the ES6 models, that they act now as a top level model. You can think of this model like an enclosing function scope when your variables and functions and let and cons declarations, they are not attached to the window object or to this global scope, all right? The other is the web service worker, where now you can have access to these global variables via the self functions, and var declaration now are attached to the self. The let and cons does not. And also is the node environment, where in node you say, hey, this is now the file that I'm going to load to the JavaScript engines. And this is quite interesting because anytime that you load that particular file, it acts as its own modules. So in other words, this different file that you're loading to JavaScript, previously as CommonJS, they don't have access to a global scope previously, right? They only have access is if those models now are referencing another models in that program. Unless, but right now, with Node version 20, version 18, we have now this global scope that we can now is put variables on top of that and share across different models. Previously CommonJS model, and now ES6 models. And then I find that this is quite interesting and revealing as well. So now that we know the scope, all right, and how that works, this is just part of the story, because we also need to understand is that how certain declarations behave. So for example, like var and functions, and that is, for example, what happens when you define them, and well, and how JavaScript treats them, which is they host those declarations at the top level of that scope. This is something that happened here in JavaScript, and yeah, I do think that's not only quite interesting, but also important to understand that how that works for certain declarations, whether it's functions or var, that they put that now at the top of the scope with undefined values, with the undefined, with the var keyword, and with the function value with the function keyword. So what happened is that as we explore this and how now, for example, the let and cons keyword behave, right? And especially instead of a functions declaration, um, because let and cons are specific syntax that allows to describe is per block, which is another scope, and that scope is only created when you use now this particular uh, syntax form of declaration, the let and cons. So that's great because there is something known as, there is a question here. So if the var and functions are rise to the top of the scope and assigned to a undefined value or the function value, depending on the declaration, so let and cons, what are they assigned? Are they doing the same thing? How now the value before the declaration of that let and cons happens? What will be the value of that reference here? And it turns out that this is known as a temporal dead zone, which is, hey, anytime that you now declare a variables, is going to be put at the top, all right? But in the case of let and cons, those values, all right, are gonna put at the top of the scope. You can have access to, and I won't assign any value to this. This is part of the behavior of JavaScript. You might wonder, why do we have this? This is also something that is not exclusively to let and cons. Var and function actually now do that, but they assign any value, and because of that, well, you can now have access to that value here. So, but the point here is that why do we have this cons and let, right? That's the main question here. And well, the thing here is that with this declaration, where the idea is that having so redeclare variables can be hard to detect, and it leads to several bugs in your programs. So avoiding redeclaration of variables in the same scope is something that is desired. So this is why now they put this let and cons. But the thing is, why you don't, for example, follow the behavior of var or functions, right? Why you don't host that with a particularly undefined value? In the case of let, all right, that makes sense with the case of cons. You say, hey, no, we don't going to do that because a constant is something that you define once, deal with that for the entire scope. But with let, why we don't have the behavior of var? Why we don't guarantee that particular behavior? So it turns out that, well, let and cons, since now they are in the same bucket, they decide to go with it. That, hey, if we are now hosting cons, so if we are not going to host cons, so let's going to also do that for the let, and then ship that to the EX6. Well, the reason to that, I go beyond the scope of today's video. You can actually take a look at that. But this is part of the decision that they have made, and why they made that decision, that it might be quite controversial and leads to a lot of confusion. So, but in any case, so here we are. To understand, so to know the hosting, all right, and how hosting works for certain declarations, and also is not only for var and function, and how and let and cons, and then how it behave with iteration syntax. So for example, while and for of and for in, as well as the traditional for. And this is why we have a lot of things with we have a lot of interview questions with this for stuff issues, to see if you actually truly know what JavaScript is doing behind the scenes, and why, for example, we don't use var in a for traditional loop, because this is a scope per functions or at the top of the global scope, right? And because we don't want that kind of behavior, that's why we use now let, because it guarantees that any time that this iteration happens, and the code needs to evaluate entering into this block, is going to create now a new variables in this particular scope. We're going to create a new scope in this functions, aka you're going to have a reference to that particular variable anytime that this scope enters here. And this is why we can now save ourselves with a ton of issues with scoping here, especially with let and cons. And this is not true with cons, because at the end of the day, you are redeclaring, you are reassigning a value, and this is not allowed for the cons. So after that, that I do find that is very revealing, absolutely. We then now talk, so for example here, of how that behave, and also is the and what the temporal that sum is, all right, that I mentioned before, is also is, well, now that we have an understanding in this, we develop the intuitions of the variables declaration and how they behave, all right, with hosting. Then we look at how now can we or why it is important for us when it comes to organize our code to limit the scope of variables. And this is for the security standpoint. Not only that, but following is this principle of least privilege from software engineering, but also is the principle of least exposure to avoid certain kind of bugs that are hard to identify and refactor. So, for example, is how do you deal with the name collision? All right. So, for example, you have now a for, and if that for you define is a variable var, so that will be globally scoped. And if for some reason at some point in a different level of your program you want to reuse that variable, the index, it might be in a different state. So therefore, it can cause problems. The other is the unexpected behavior when you now expose variables, or when you now assume that variables can have is a particular type. This is especially true for plain JavaScript. If you're growing with TypeScript, that's not the case. Okay. And what's happened there is how do you, so for example, when that happens, when you assume that, for example, if you receive an array of numbers and then somehow you receive now well, an array of booleans or strings, so your algorithm might not work as expected. And the other is that unintended dependency, which is if you expose a lot of these behaviors, it'll be quite hard to let down the road is refactor that to hide that variables that you don't want to expose, the private variables, for good or ill-intent developers. So you can do is just versioning that particular code. All right. So in any case, this is not the problems of overexposing variables in a different scope. So we look at how can we do that with let and cons, and also with function scope, and known and getting here into now save us time to compute code with memorization, and also is with the how do you put it? Also is with the exactly, and also is with this immediately invoking function expressions. So again, so what we're doing here is that because we don't want to we want to avoid is overexposing of variables, all right, by enclosing that in a particular scope with let and cons, or by wrapping that functionality into a immediately function expressions, and depend of the use case, you can now is save from these particularly problems. And the other is with functions in scope. So scoping with blocks to prevent this overexposing of variables, and the other is function scope. Functions, because catch is also allow you to not redefine that. That's right. And also is exactly, and also is functions declarations in block. So again, by not exposing or by limiting these scope exposures, we can now prevent ourselves from these particular issues. So by blocking scope, by using immediately function expression, and also is to avoid is the function declarations in blocks, right? Because this can lead to several unexpected behaviors across engines, right? So we are looking at this function declaration in block just to understand why we should be avoided function declaration in scope. And if you do find yourself in the need of wrapping that inside of a scope, it is preferred to then define that as a variable, as a function expressions, and then now evaluate that if you need to. Because again, the thing here is that declaring is functions inside of block, it might lead to unexpected behavior. It's not working the way you might expect, or according to the logic of the functions, or the logic of the functions declarations behaviors. For example, like hoisting. This is why we should avoid this, right? And finally, we are now here on the chapter 7 is using closures. Up to this point, we have focused on the ins and out of lexical scope and how affect the organizations and usage of variables in our programs. Our attention again shifts broader in abstractions to the historically somewhat daunting topic of closures. So don't worry, you don't need an advanced computer science degree to make sense of it. Our broad goal in this book is not to merely to understand scope, but to more effectively use it in the structure of a program. Closure is central to that effort. How can we use now this? How can we structure programs effectively? Recall the main conclusion of chapter 6, the least exposure principle, encourage us to use block and functions to limit the scope exposure of variables, right? And this help keeps code understandable and maintainable, and helps avoid many scoping pitfalls. So, for example, name collisions, unexpected behaviors, and overexposing of variables that are hard to refactors on the way, which is exposing unintended dependencies. So closure built on this approach for variables we need to use over time instead of placing them in large outer scope. We can encapsulate more narrowly scope them but still preserve access from inside functions for broader use. Okay, closer builds on this approach. For variables we need to use over time instead of placing them in a large outer scope, we can encapsulate more narrowly scope them but still preserve access from inside functions for broader use. Functions remember these reference scope variables via closure. So we already saw an example of this kind of closure in the previous chapter as factorial in chapter 6, and you have almost certainly already used it in your programs. If you ever written a callback that access variable outside of in its own scope, if you have written a callback that access variables outside of your own scope, guess what? Exactly. That's a closure. So closure is one of the most important language characteristics ever invented in programming. It underlines major paradigms including functional programming, modules, and even a bit of class-oriented design. Getting comfortable with closure is required for mastering JavaScript and effectively leveraging many important design patterns through your codes. Again, because the more you align to the JavaScript and how this behave, how this work, the more effective you will be with your code, the more effective you will need to implement features or maintain the code. Addressing all aspects of your closures require a daunting mountain of discussion and code throughout this chapter. And make sure you take your time and ensure you are comfortable each bit before moving into the next. Okay. So we have a lot of this. Okay, good. Closure life cycle and garbage collections. Diggy. An alternative perspective, which is good. Why closures, which is also good. Closer to closure. And the other is a chapter 8, right? Just to look at this. The model pattern, encapsulation and least exposure is often cited as a principle of object-oriented programming. No, I'm gonna read this. Encapsulating of least exposure. So what is a model? Namespace stateless grouping. Data structure stateful grouping. Namespace. Okay, namespace, not a model. Data structure stateful grouping. Okay, stateful grouping, models, stateful access control. All right, model factory, multiple instance. Exactly. So you can now receive this record, get the name, return this public API. All right, which is the function, and then returns that. So anytime that you define the student here, you're gonna get that because you define this data here, Node CommonJS model as it is, and this one. Okay, forward, and that's it. All right. I do think that will take much more time. Okay. Um, that's interesting. Okay. Um, okay. All right. Okay. So the TLDR is that I'm looking is at closure. It's just to understand is the nature of the language to be much more effective when I need to use this tool, aka when I need to implement features, when I need to update, when I need to implement a feature based on some client, yada yada yada. When I need to implement a feature, when I need to provide maintenance to this, and when I need to organize the code in a more in a way that all the hard work of women and men throughout computer science history have made to say, this is our conclusion, bro. Pal, hey Paul, yes, this is our agreement here. So based on all of our efforts and sweat and blood and yelling and bosses yelling at us we cannot iterate fast and quickly, la, 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 yada 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 yada. So we come up with this, right? Which is a combination of mathematical definition, mathematical definitions, and some other like object definition here. Absolutely. See the closure. Closure is originally a mathematical concept from lambda calculus. Lambda calculus. What is lambda calculus? What lambda calculus is? A lambda calculus, also written as this, is a formal system for expressing computations based on functions, abstractions, and applications using variable bindings and substitution. There is a lot of doing. It was introduced by the mathematician Alonzo Church in 1930. Was an American computer science mathematician, logician, and philosopher who made major contribution to the mathematical logic and the foundation of theoretical computer science. He is best known for the lambda calculus. Holy Alonzo Church. You know, all of this heavy stuff has been made by people like him that they have dedicated time to this. All right? Holy moly. Where they say, hey, I now... This is the approach, right? This is a particular approach based on the observable reality, based on the thing that we can learn from that. That's where the mathematic word come from. We can, or he described is that, hey, this is what give us now is this predictability of doing this stuff. All right, this reliance on this stuff. The lambda calculus emerged in 1936 paper showing the unsolvability of the ancient Dunes problem. This results precedents Alan Turing worked on the halting problem, determining from a description of an arbitrary computer and an input whether the program will finish running or continue to run forever. The halting problem is undecidable, meaning that no general algorithm exists to solve this. Okay. So, but in any case, the lambda calculus influenced the design of Lisp and functional programming language in general. The church encoding is named the church encoding is named in his honor. In his honor, Alonso Church Award for Outstanding Contribution to Logic and Computation was established in 2015 by the Association for Computing Machinery Special Interest Group for Logic and Computation, the European Association for Theoretical Computer Science, the European Association for Computer Science Logic, and the Kurt Gödel Society. The award is for an outstanding contribution to the field published within the past 25 years and must not have yet received recognition via another major award such as Turing Award, the Paris Kanellakis Award, or the Golden Prize. Church also made contribution to the theory of random sequence. Church elaboration of a methodology involving the logistic method, his philosophical criticism of nominalism, and his defense of realism. His argumentation leading to conclusion about the theory of meaning, and the detailed construction of the Phrygian and Russellian intentional logics are more than sufficient to place him high up amongst the most important philosophers of this century. Over the course of his academic career, Church oversaw 31 doctoral students. Many of them have led distinguished careers in mathematics, computer science, and other subjects, including Peter B. Andrew, George A. Barnard, David Berlinski, William W. Bone. I have barely heard about him. Martin Davis, Alfred L. Foster, Leon Henkin, John G. Kemeny, Stephen C. Klein, and founder of the branch of mathematical logic known as recursion theory. Oh my fucking Simon B. Koch, number theory and quantum mechanics. Maurice Liabe was a Canadian-American mathematician. Gary R. Mark, Michael O. Rabin, Israeli mathematicians. Nicholas Research, Harley Rogers, J. Barclay Rosser, Dana Scott, Raymond Smullyan, concert pianist, logicians, Taoists, and philosophers. What the hell is in this, bro? Taoism, what the hell? Holy, 97 years, god damn it. Alma Mater, University of Chicago, Princeton University. Fields logic. Okay. Smullyan wrote several books about Taoist philosophy, a philosophy he believed neatly solved most of the traditional philosophical problems, as well as integrating mathematics, logic, and philosophy into a cohesive whole. One of the Smullyan discussions of Taoist philosophy centered on the question of free will and imagined conversations between a mortal human and a god. Okay. Holy moly. Knights and knave, involving knights who always tell the truth and knave who always lie. Okay. Knights and knave. Okay, so there are some logic problems. No, okay. Because we're gonna get it. So you are the founder of the recursion theory, which subsequently helped to provide the foundation of theoretical computer science. Klee works ground the study of computable functions. But again, this is not what we're looking here. This is not what it's meant to. And Alan Turing. Holy hell, Alan Turing as well? In addition to those he directly supervised, Church also had a large influence on other mathematicians and computer science. Haskell Curry, who expand on Church's idea with the concept of Turing, stated that one of his textbooks, Introduction to Mathematical Logic, first published in 1944, was written with the meticulous precision would characterize the author's works generally. Holy moly. The introduction of lambda calculus. All right. Decision problems. So again, this lambda calculus is describing is this. It's a formal system for expressing computations. And this is what you look at this. This is a formal system for expressing computations based on functions, abstractions, and applications using variable bindings and substitution. On type lambda calculus, the topic of this article is universal machines. On type lambda calculus, the topic of this article is universal machines, a model of computation that can be used to simulate any Turing machine, and vice versa. And Turing machine is a mathematical model of computation describing an abstract machine that manipulates symbols on a string of a table according to the table of rules. So despite the model's simplicity, it's capable of implementing any computer algorithm. So it is a universal machine that can be used to simulate a Turing machine, a machine that is capable of implementing any computer algorithm. Okay. It was introduced a computer that can implement, or a computer is a model of computation that can be used to simulate a machine that can implement any computer algorithm. That's what the machine. So any sequence of values here. Holy moly. So a Turing machine is a machine that can implement any computer. It's a machine that can implement any algorithm, any computer algorithm. Any sequence of steps, any sequence of computational steps. Holy hell. I don't know what they smoking, bro. I don't know what they smoking, bro. Definitely, I don't know what they are smoking, bro. So well, in any case, but it's this. But it's this. It is very unless the only way you can actually figuring out this is by accessing to that, by actually is getting into this. It's a simple notation for functions and applications. It's a way of how you can describe is functions and application. Okay. Well, so but I'm not going to list out of math formula or use a bunch of notation and jargon to define. Instead, I'm going to focus on a practical perspective. We'll start by defining closures in terms of what we can observe in different behaviors of our programs, as opposed to if closure was not present in JavaScript. However, later in this chapter, we're gonna flip closures around to look at it from an alternative perspective. And closure is a behavior of functions and only functions. If you aren't dealing with a function, closure does not apply. An object cannot have closure, nor does a class have closures. Though it is function method might, only function have closures. So for closures to be observed, a function must be invoked. And specifically, it must be invoked in a different branch of a scope change from where it was originally defined. A function executing in the same scope it was defined will not exhibit any observably different behaviors with or without closure being possible. By the observational perspective and definition, that is not a closure. Let's look at some code annotation annotated with its relevant scope bubble color, chapter 2. So you get is this. So this is the outer global scope, the inner function global scope, the another inner function global scope, and there you got it, right? It's a choosing student. When you call this choosing student to name, it's going to now is call that function. All right, when you call that function and provide the student ID, then because this function has been already called with this value here, is going to execute that. It's going to create a new function execution context that is going to now is first resolve the identifier of these variables, all right, and then it's going to execute the code. So for example, is assigning this value to the student, and then it's going to now return a function here where now this function will have is this. So you create a new function scope, okay, that this is going to now find is a student ID. Okay, here you're creating now a closure of the student, and then you're going to return now this one, right? The greeting dot student dot name. And here we're saying is, hey, I do want to access the function name, and in this case is this greet student. Exactly. So when you now call that function and you pass that, it's gonna give it to you now this hello Sarah and hello Frank. The first thing to notice about this code is that the lookup student outer function creator returns an inner function call. greet student, look up student, it called twice. So, but in any case, I'm gonna leave this as it is. Take care. Bye bye.